Single-dimensional domains, job scheduling. As a first example for the interaction between game theory and algorithmic theory, we consider single-dimensional domains. Simple single-dimensional domains were introduced in Chapter 9, where every alternative is either a winning or a losing alternative for each player. Here we discuss a more general case. Intuitively, single-dimensionality implies that a single parameter determines the player's evaluation vector. In Chapter 9, this was simply the value for winning, but less straightforward cases also make sense. Scheduling related machines. In this domain, n jobs are to be assigned to m machines, where job j consumes pj time units and machine I has speed si. Thus, machine I requires pj over si time units to complete job j. Let Li equals to the summations of pj summing for all index j such that j is assigned to I. Be the load on machine I. Our schedule aims to minimize the term max of Li over Si maxima, where the maxima is taken among all possible I, the make span. Each machine is a selfish entity, incurring a constant cost for every consumed time unit, and without a loss of generality, assume this cost is 1. Thus, the utility of a machine from a load Li and a payment Pi is minus Li over Si minus Pi. The mechanism designer knows the processing times of the jobs and constructs a scheduling mechanism. Although here the set of alternatives cannot be partitioned to wins and losses, this is clearly a single-dimensional domain. Definition 12.1. Single-dimensional linear domains. A domain Vi of player I is single-dimensional and linear if there exist non-negative real constants. The loads the set of Qia for all little a, which is in capital A, such that for any little vi in capital Vi, there exists C in R minus the cost, such that Vi of A is equals to Qia times C. In other words, the type of a player is simply her cost, C, as disclosing it gives us the entire valuation vector. Note that the scheduling domain is indeed single-dimensional and linear. The parameter C is equal to 1 over Si, and the constant Qia for alternative A is the load assigned to I according to A. A natural symmetric definition exists for value maximization as opposed to cost minimization problems where the types are non-negative. We aim to design a computationally efficient approximation algorithm that is also implementable, as the social goal is a certain min-max criterion and not to minimize the sum of costs. We cannot use the general VCG technique since we have a convex domain. Chapter 9 tells us that we need a weakly monotone algorithm. But what exactly does this mean? Luckily, the information of weak monotonicity can be much simplified for single-dimensional domains. If we fix the cost C minus I declared by the other players, an algorithm for a single-dimensional linear domain determines the load Qi of C of player I as a function of her reported cost C. Take two possible types C and C prime and suppose C prime is greater than C. Then the weak monotonicity condition from chapter 9 reduces to minus Qi of C prime times C prime minus C, which is greater than or equals to minus Qi of C times C prime minus C, which holds if and only if Qi of C prime is less than or equals to Qi of C. Hence, from chapter 9, we know that such an algorithm is implementable if and only if its load functions are monotone non-increasing. Figure 12.1 describes this and will help us figure out the required prices for implementability. Suppose that we charge a payment of Pi of C equals to the integrations of Qi of x minus Qi of C, integrating starting from 0 to C and integrate dx. From player I, if he declares a cost of C. Using figure 12.1, we can easily verify that these prices lead to incentive compatibility. Suppose that player I's true cost is C. If he reports the truth, his utility is the entire area below the load curve up to C. Now if he declares C prime, some C prime which is greater than C, his utility will decrease by exactly the area marked by A. His cost from the resulting load will indeed decrease to C times Qi of C prime, but his payment will increase to be the area between the line Qi of C prime and the load curve. On the other hand, if the player will report C prime prime which is less than C, his utility will decrease by exactly the area marked by B, since his cost from the resulting load will increase to C times Qi of C prime prime. Thus, these prices satisfy the incentive compatibility inequalities, and in fact, this is a simple direct proof for the sufficiency of a load monotonicity for this case. The above prices do not satisfy individual rationality, since a player always incurs a negative utility if we use these prices. To overcome this, the usual exercise is to add a large enough constant to the prices, which in our case can be the integration of Qix dx integrating starting from 0 to infinity. Note that if we add this to the above prices, we get that a player that does not receive any load, i.e. declares a cost of infinity, will have a zero utility. And in general, the utility of a truthful player will be non-negative, exactly. Integrations of Qi of x dx integrating starting from C to infinity. From all the above, we get the following theorem. Theorem 12.2. An algorithm for a single-dimensional linear domain is implementable if and only if its load functions are non-increasing. Furthermore, if this is the case, then charging from every player I a price Pi of C equals to the integrations of Qi of x minus Qi of C dx, integrating starting from 0 to C, minus the integration of Qi of x dx, integrating starting from C to infinity, will result in an individually rational dominant strategy implementation. In the application to scheduling, we will construct a randomized mechanism as well as a deterministic one. In the randomized case, we will employ truthfulness in expectation. See Chapter 9, Definition 9.27. One should observe that from the discussion above, it follows that truthfulness in expectation is equivalent to the monotonicity of the expected load.